Now we'll discuss intrinsic semiconductor Fermi energy, like the Fermi energy of intrinsic semiconductor. As we know that in intrinsic semiconductor, the number of electron in the conduction will be equal to the number of holes in the valence band. Now we know that the number of electron in the conduction band is equal to Nc e raised to a power EF minus EC over kT, and the number of holes in the valence band is given by Nv e raised to a power EV minus EC over kT. We already derived these relations. Now using these two relations here, we get Nc e raised to a power EF minus EC over kT, which is equal to Nv e raised to a power EV minus EC over kT. Now if I bring this factor to this side and this factor to that side, we get e raised to a power minus e raised to a power EF minus EC over kT into e raised to a power minus EV minus EC. No, sorry, this is EV minus EF. Yes, EV minus EF. So this will be equal to EV minus EF over kT, which is equal to NV over NC. Exponential of minus EC minus plus EV minus 2EF over kT is equal to NV over NC. If we take the natural log of both sides, then the natural log will cancel with this exponential factor. So we left with EC plus EV minus 2EF over kT, which is equal to natural log of NV over NC. If we rearrange this factor, we get EF is equal to EC plus EV over 2 multiplied by kT over 2 into ln NV over NC. Just bring this factor to this side and divide by 2, we get this relation. Using value of NC, using value of NC and NV, which are NC is 2 into 2 pi m e steric kT over h square whole 3 divided by 2, and NV is 2 into 2 pi mh steric kT over h square whole 3 divided by 2, and the above expression EF will be equal to EC plus EV over 2 into 3 kT over 4 ln mh steric over mh steric, the effective mass of holes over effective mass of electron. But we represent the Fermi energy of intrinsic semiconductor, but Fermi energy of intrinsic semiconductor is represented by EI. So we have EI, which is equal to, we have two expression for the Fermi energy. One is this in terms of effective density of states, and the other one is in terms of effective mass of electrons and hole. So EI is equal to EC plus EV over 2 into kT over 2 ln NV over NC. And the other relation is this one. EA is equal to, we replace EF by EI, which is equal to EC plus EV over 2 into 3KT over 4 ln MH steric over ME steric. So we have these two relations, which I will write it here. EI is equal to EC plus EV over 2 plus KT over 2 ln NV over NC. And the other relation is EC plus EV over 2 plus 3KT over 2 ln MH steric over ME steric. This is the Fermi energy in terms of density of states, effective density of state, effective density of states, and this is the Fermi energy in terms of effective masses of electron and hole. Now we consider different cases. The first case is when we suppose that the mass of the hole is greater than mass of electron. It means that effective density of hole is greater than effective density of electron. Then this implies that ln MH steric over ln ME steric will be greater than 0, or ln NV over NC will be greater than 0. So if it is greater than 0, then EI should be EC plus EV over 2 plus some factor. So suppose we have this conduction band and we have valence band, and here we have the Fermi energy EF. So this is EC and this is EV. Now EC plus EV over 2 will give us this line. It is the middle of this conduction and valence band. But here we have this extra factor, this factor, okay, which is positive for the first case because it's positive, so its value should be 0.1 or 1 or some value. If we add this value with this factor, then the energy, Fermi energy of intrinsic semiconductor will shift above this line. So we have EI here. So it means that the Fermi energy of the intrinsic semiconductor in the case when effective density of hole is greater than effective density of electron will shift towards conduction band, and the shifting is by this factor. Now the second case is when MH steric mass of hole is, effective mass of hole is equal to the effective mass of electron, or in other words, the effective density of electron is hole is equal to effective density of electron. Then in that case ln MH steric over ME steric will be equal to 0, or ln NV over NC will be equal to 0 because they are equal. So log of 1, natural log of 1 is always equal to 0. Natural log of 1 is always equal to 0. So in that case, our expression for the effective density of state EI is EC plus EV over 2 because these factors are 0. If these factors are 0, then the Fermi energy of intrinsic semiconductor will be given by this relation. So it means that in this case, this is the conduction band and this is the valence band. This is the top of the valence band and this is the bottom of the conduction band. And the intrinsic Fermi energy of intrinsic semiconductor will exactly lie above this Fermi level, EI. So this is the conduction band, this is the valence band. EI is EC plus EVO2, which is exactly lie above this EF. Now we have the third and last case, which is if effective density of hole is greater than, no, is less than, sorry, we already considered the greater case here, is less than effective density of electron, or in effective mass of holes is less than effective mass of electron, or effective density of hole is less than effective density of electron, then the natural log of NV or NC, which is less than 1, will be less than 0, or ln effective density of hole or effective density of electron, which is also less than 0, this factor, and the natural log of some number which is less than 0 is always less than 0. Is less than 1, sorry, this factor is less than 1, this factor is less than 1, so this factor is also less than 1, and natural log of a factor which is less than 1 is always less than 0, so its value is negative. Now if this is negative, then we have this expression EC plus EO2 EVO2 minus some factor, so the minus factors comes here, so in that case we have the valence band, we have the conduction band, this is the bottom of the valence band, conduction band, this is the top of the valence band, and we have the Fermi energy EF here. Now EF is exactly this one, but here we have a factors minus something, so it means that the value will be somewhere here. So this is the intrinsic Fermi energy level of intrinsic semiconductor, which is shifted below this actual Fermi energy level by this factor, by this value. So this is all about Fermi energy of intrinsic semiconductor. Thank you.